Today we will construct a model to predict the motion future using Newton's second law in a case where we'll need to apply our new understanding of fundamental interactions. The case we'll choose is familiar. We will build a computer model of the Earth's orbital motion around the Sun. Now, in this case, we will assume the gravitational force of the Sun on the Earth is the only significant interaction. Now, there will be some new things to learn here. However, with the modeling experience that you have just acquired from earlier lectures and lab work, you'll discover, we believe, that there's a lot you already know about how to solve this problem. And we'll begin, as we always do, with starting from a fundamental principle, Newton's second law. So in fact, let's start here, and let's first recognize that to predict the motion of our system, the Earth, we need to know the Earth's mass, and to describe the total force on the Earth due to the Sun, we need to know Newton's law, need to use Newton's law of universal law of gravitation, and so to specify that interaction, we'll need to know the universal gravitation constant, big G, the mass of the Sun, and an initial estimate for the magnitude of the relative position vector, which locates the system, the Earth, with respect to the source of the gravitational force, the Sun. Here we will take, for starters, as the average distance from the Earth to the Sun. Now, all these quantities you can easily look up, along with the mass of the Earth, by searching the internet. And speaking of the Earth's mass, notice that the force depends on this system property too. But let's be clear. The source of the force is the Sun and the surroundings. No Sun, no gravity force, even though the Earth would still have the property of mass. Now we start by launching VIDLE and open the same VPython program, lab1start.py, that we used both for Lab 1 and for our earlier model of the constant velocity motion of a soccer ball. As always, we encourage you to work through on your own the steps we discuss here. You can download another copy of this and all supporting Python programs here. As always, it's a good idea to run the program to make sure we're ready to start. It may seem surprising and amazing that we can use the same starting point for modeling the motion of both a soccer ball and a little bit larger ball, a planet. And it is amazing, but that's the power of starting from a fundamental principle. First, let's look at this portion of the starter program containing lines of code that provide the initial setup for different representations of the motion we're modeling. Notice that this line sets up the object representing the system. So what we'll do is let's rename this line to be more descriptive, describing the Earth rather than a soccer ball. Now, there are several places in the code where we need to make this change. So the best way to do this is all at once. We can do this by going to the Edit tab in the VIDLE code window, selecting the Replace option, and then in the appropriate places we type in the word ball, which we're going to replace with the word Earth. And then we can hit the option Replace All. I'm not going to complete this here as I already did this earlier. And if you do so, you should see changes which should look like this. Now, we've also changed the label of our origin marker here. We've changed that to indicate the Sun. Because for our choice of coordinate system, we're going to place the Sun at the origin. Now, in this visualization setup, there are several places in the code where we need to set appropriate length scales so that we can see the visualized objects. Right now, the length scale for both the full visualization window as well as for all the visualization objects are given in meters or fractions of a meter. we need to change these to astronomical scales related to the magnitude of r, the average Earth-Sun distance, since that is the length scale over which we are modeling the motion. So we've done this in this code, where we've set the display window to be something somewhat larger than this Earth-Sun distance, and we've set the length scale of the different objects to something like 1 to 10% or so of this Earth-Sun distance. Let's emphasize that the main consideration here is to choose the length scale so we can see what's happening in our visualization window. So we don't have to be very precise here. None of these choices will affect the physics of the motion we will be modeling. By contrast, the next lines of codes that we will need to edit, the system properties and initial conditions, do impact the physics. So we have to be careful here. Here we're showing the code after the correct edits have been made. Clearly, we need to indicate, in this case, the mass of the Earth, as we've done so here. With the Sun located at the origin of our coordinate system, the Earth should be initially located at the average Earth-Sun distance away. Now, we have the freedom with our choice of coordinate axis orientation to choose to put the Earth initially on the x-axis at the appropriate distance, Earth-Sun distance. And that's what we've chosen. And we've done that at our initial chosen time, t equals 0. Now, as we've learned earlier, we also need to set an initial velocity to make predictions using Newton's second law. The magnitude of that velocity we can set to the Earth's orbital speed, 30,000 meters per second, which we can also find on the internet. However, we need the velocity vector, which means we need an initial direction. We're going to make a choice here. Have the initial velocity be 30,000 meters per second pointed in the plus y direction for our choice of the initial position of the Earth. Let's see what happens when we make these choices and we run our computer model. We will revisit this choice a little later in our lecture. Now, at this point, you can, if you're doing this at home, you can run your code and you should see something like this, except that for the labels and the axes, which I drew in by hand. You should not see any motion as yet, as we have not yet put in the interactions or Newton's second law yet. We still have more initialization to do. Let's plan to run our model for a year in simulation time, which is the time scale over which we expect the Earth's orbit to move a lot. So we need to choose delta t to be small compared to that. Here we show choosing that time scale to be an hour, given and expressed here in seconds, since we want to keep everything we express in the same SI system of units. Now, remember, while an hour seems long to us on everyday scales, we always look to the natural time scale of our problem to tell us what small is. So, compared to the year that we're going to use to predict over, an hour is small. Next, we have to put in some initialization information for describing the gravitational interaction. We need still the Sun's mass and the universal gravitation constant. So let's add lines of code that do that right here. Now we are in a position and ready to apply Newton's second law iteratively in a while loop. Notice here we've already put in the correct code for Newton's second law to update the velocity of the Earth, and we have the correct code to update the position of the Earth. The problem here is we don't have the correct expression for the net interactions, so we need to fix that. First, let's properly set, though, the length of time we'll be making predictions. We're setting that as an integer multiple of delta t, which, as we said, is 1 hour. So for this way of expressing it, we have our time over which we will be making predictions to be 1 year. Now let's put in Newton's universal law of gravitation. We're going to do this in a few separate steps. First, we need to calculate the relative position vector r, along with the magnitude and unit vectors associated with r. And we have shown the code here for doing that. Notice that here we are using a Python function called mag to find the magnitude of the vector r. Notice also that even though the sun is at the origin, so sun.pos is the 0 vector, it's good form to put in the full definition for r, which is always in terms of the system position minus the position of the source of the force. We do this just to remind ourselves of the meaning of the relative position vector r. Now we're ready to express Newton's gravitational law in Python code. Give that a try. You should end up with something like this. Now, since the gravitational force is the only force, then we put in a line to set the net force, F net, to be equal to this only force, the gravitational force. And now our model is complete. So now let's run it and see what happens. So what we would expect to see is that over the time of a year, from our common knowledge, the object representing an Earth should make one round trip in a circular orbit. And in fact, that's what we see in our simulation. So that's nice. Now let's remember how predictions are actually made. We make them one small time step at a time, 1 hour at a time, repeated over and over again. So what we see, the motion that we see, is the accumulation of all those 1 hour predictions made over a simulated time of 1 year. Let's also remind ourselves that in order to make good predictions, we need to have the right initial conditions we show here. Imagine, though, for example, we keep everything the same, even the same orbit speed, but change the initial conditions somewhat. Say, instead of having the initial y velocity pointed in the plus y direction as shown here, let's tilt that y velocity somewhat, something like 30 degrees. Then making only this change to the initial velocity in our code, that is, setting the initial velocity to the velocity vector shown here, let's see what kind of prediction we would end up making. What we see is that the motion is very different. You can play around with initial conditions with your model to explore the motion of the Earth in an alternate universe like this. And you will see that for the same specific gravitational force law, that there are lots of possible motions of these alternate Earths, almost all of which are too close to or too far from the sun to support life as we know it. The actual motion of the Earth around the sun is pretty close to what we call uniform circular motion. We will discuss this in more detail as part of a general discussion of what we'll call curving motion, which we will cover in a few lectures.